today. Okay. So I personally invited him and asked him to give this this seminar because well, we were both very much engaged in pushing quantum computing in Spain. So Elias comes from the University of Oviedo. He's both a mathematician and computer scientist. He did his PhD in 2001. He's been in Russia with collaborators, and his current research focuses in how to apply quantum computation to algebraic optimization, data analysis, and machine learning. So he's now very much engaged with CERN. So he's, as he just told me, he got in contact with people in CERN here in Santiago last year, and then he went there, very courageous, and then he started collaborating. And since then, I think you have produced several papers with CERN people on application of quantum computing to data analysis. You will probably tell us something about this. So he's currently in the advisory board of the CERN Quantum Technology Initiative, and he's in the advisory board of the Quantum also, which is an initiative for gender issues in quantum technologies. And now he's president of the Spanish think tank that also pushes quantum computing all over Spain. This is mainly our main point of contact, which is called QSVM. And well, that's almost all I wanted to say. And I wanted to thank you again. And please tell us something about this interesting stuff.
Okay. Well, good morning, everyone. And first of all, I would like to thank the organizers of the seminar for this invitation, especially Javier Mas, also for the nice introduction. It is really a pleasure to be here, sharing with you my passion for quantum computing, and I hope that you find the talk interesting. I will be mainly focusing on what is quantum computing and what are the possible applications, or what we think are the possible applications of quantum computing, with a special emphasis in high energy physics. So to motivate the talk, oh, what's happening here? To motivate the talk, I did a simple but I think interesting exercise, which is to Google quantum computing news. Okay, and I collected here several of the headlines that I found online, just in the first or two first pages in a Google search about what is the news in this quantum computing field. And here you can see that, well, there are a lot of different headlines regarding investments, regarding the interest of banks and different companies and different governments who are pushing quantum computing and searching for an advantage with quantum technologies in different fields. Okay, so, well, of course, you already know also about news in the last 1-2 years about obtaining what is called quantum supremacy or quantum advantage with quantum computers. And I think that this situation, which is kind of being accelerating in the last few years, it's very interesting to anyone who is in science or who uses computing in a heavy way for analyzing data or for doing research. Okay, so I think this is a way of motivating why we are interested, or why we could be interested in quantum computing, and to try to see why all this money is being poured into this research, both by companies and by governments. I want to first define what is quantum computing and try to highlight the difference of quantum computing to classical computing, to try to understand a little bit better what is different with quantum computing, what quantum computers can offer us as scientists in order to speed up our computational tasks. Okay, so the first thing that I want to do is to define what is quantum computing. And probably my favorite definition is the one that I'm showing here in the slide, that says that quantum computing is a way of doing computing, of doing calculations that explicitly uses properties of quantum mechanics, like superposition, entanglement, interference, the principle of the Heisenberg principle, and so on, in order to speed up calculations. Okay, and well, this is kind of the definition that I usually adopt regarding quantum computing, but it is a little bit misleading, because you can argue that, well, in fact, every computing device is based on the laws of quantum mechanics. Every physical computing device, in fact, needs to obey quantum mechanics, and somehow uses superposition, entanglement, interference, and so on. But the main key here, or the main point here, is that in this way of doing computation, we explicitly use these different properties in order to do our computations in a different way. Okay, in order to model what we can do with this explicit use of superposition, entanglement, and interference, several different models of what is quantum computing have been proposed, starting in the 80s and 90s of the past century. And for instance, one of the first models was the model introduced by David Deutsch, which is called the quantum Turing machines, which is similar to the classical model of computing that we all know, Turing machines, but explicitly uses superposition, interference, entanglement in order to do computations. The problem with this model is that it is very difficult to implement in practice. So in the last few years, or in the last 2 decades or so, all the different models have been proposed, which are easier to implement in practice, but that also capture these properties of the original quantum Turing machines. And all these models are mathematically equivalent, so we can compute exactly the same functions with all of them. But some of them, like for instance, quantum circuits, which is probably the most popular model of quantum computing, can now be implemented with actual devices, with actual physical computing devices. And I will be telling you a little bit about this later, okay? So all these models, quantum Turing machines, quantum circuits, measure-based quantum computing, adiabatic computing, topological quantum computing, all of them are equivalent. And in fact, it is a little bit surprising that they are also equivalent to classical models. So it's easy to show that you can simulate any of these models with a classical device. So the difference is not in that we can compute new functions with any of these models, but that some of these functions can be computed faster, or at least we think that they can be computed faster. This is something that we have evidence of, but we have not been able to prove rigorously mathematically yet. But we have a strong evidence that some of the capabilities of quantum computers go beyond what is possible, at least efficiently, with classical computers. So in order to give a general view of what is possible and what is not possible with quantum computing, what is more efficient with quantum computing than with classical computing, I have included here this diagram in which we have several different well-known complexity classes, in which we have, for instance, P and MP. As you know, P is the class of problems that, roughly speaking, we can solve efficiently with classical computers. MP is the class of problems whose solution we can verify efficiently with classical computers. And then we have this new class here, BQP, bounded quantum polynomial time problems, which can be solved efficiently with quantum computers. And what we believe, as shown here in this picture, is that this new class, what is possible to be computed with efficiently with quantum computers, includes, of course, everything that is possible to be computed with classical computers, but some new problems that we cannot expect to solve efficiently with only classical resources. Here, for instance, we could have, I will be mentioning some of these problems, we could have the famous problem of factoring large integers, which has a lot of interest because it directly connects with problems in cryptographical protocols like RSA and elliptic curve and things like that. But we expect also to have problems here in BQP, which are related to, for instance, simulation of physical materials, simulations in chemistry, optimization problems, and so on. In fact, there are not so many quantum algorithms that have been shown to have some advantage over what is possible with the classical algorithms that we know, we currently know. But here I have listed some of the most important ones. For instance, of course, we have factoring and the computing of discrete logarithm by what is called Shor's algorithm, which, as I have mentioned, has a lot of repercussions in cryptography. But we also have this nice algorithm, which is called Grover's algorithm, which speeds up quadratically the problem of searching in a database. We also have some algorithms to, under certain conditions, solve linear systems exponentially faster than what is possible with classical computers. We also have applications, I will be mentioning some later on quantum machine learning, on simulation of chemical processes or physical processes, and also applications in optimization with different methods. For instance, with digital quantum computers, circuit-based quantum computers, but also with what are called quantum annealers. So this is kind of the situation now, and this is what we are exploring. I need to mention that there is no practical problem as today that can be solved more efficiently with quantum computers than with classical resources. This is mainly because the computers that we have now are still noisy, are still small in the number of qubits, in the capacity of processing information. But at least we have some mathematical theorems that show that in certain cases, when we build quantum computers that are fault tolerant, that are big enough, we will be able to solve some of these problems faster than what is possible with classical computers. And well, this is the mathematical way of defining and studying quantum computers, but of course we are also interested in physically implementing quantum computers. I'm not an expert in the physical implementation of quantum information processing devices. As Javier mentioned, my background is in mathematics and computer science, not in physics. But at least I wanted to mention that there are several different technologies that are being explored, that are being researched in order to implement these quantum computers physically, and to try to scale up to situations in which we can apply these algorithms that we theoretically know will offer some advantage. Two of the most popular one, or the most developed nowadays, are superconducting circuits and trapped ions. each of them has its advantages and its problems. For instance, superconducting circuits are kind of well developed because the classical industry for computing devices has developed some methods that can be used also to construct these superconducting circuits. But also we have the problem of trying to scale up these superconducting circuits, because they need to be kept at a very low temperature, almost absolute zero, and it's difficult to isolate them from the environment and prevent decoherence, prevent the influence of external noise and so on. Okay, trapped ions are another possibility for implementing these quantum computers. They are more stable, but they are also slower, and it's also difficult to scale up these quantum computers based on this technology. And there are other technologies that are being explored. For instance, it is not mentioned here in the slide, but in China, recently there have been some nice developments with photonic quantum computers that can offer also some kind of advantage over what is possible with just classical resources. And well, to me, the most important thing is to notice that there are several different computing or competing technologies, and that the environment or the community is trying to find one that is the best one to implement these quantum computers. For instance, here I'm showing what a quantum computer based on superconducting circuits looks like. This is implemented by IBM, and in fact, this kind of device is accessible for free online. You can just register at IBM Quantum Experience and start running quantum algorithms on these quantum computers. And the quantum chip, the chip that contains these superconducting circuits, is just at the bottom of all this whole structure. The rest of the structure is used to keep the chip at a temperature which is more or less of 10 millikelvin, something like that. And then we have some devices to control the pulses that we need to send to the circuit in order to implement the different operations. Okay, when this is working, this cylinder covers the whole structure in order, of course, to isolate completely the computer and to prevent unwanted entanglement with the environment. Okay, and this kind of quantum computer is based on the model of quantum circuits that I mentioned earlier, and I would like to explain a little bit what is the basis of programming, how to program one of these computers. And to that, we need to introduce some concepts which are used in this model of quantum circuits, which more or less correspond to the three main components of any algorithm, either classical or quantum. For instance, to start with, we have some data that we want to compute with. Then we perform some operations on this data, and finally we obtain some results. So this is kind of the natural way of doing some computation. We start with data, we perform some operations, and then we get some results. In the quantum circuit model, data is stored in what we call qubits that I will be defining in a minute. Then we perform some operations on the states of these qubits with what we call quantum gates, which are just unitary transformations of a certain kind. And then to obtain the final result, the output of the algorithm, we need to measure. We need to perform a physical measurement of the state of the system in order to obtain a result. So I would like to give some details on what are qubits, what are quantum gates, what are measurements, in order to understand what is different in quantum computing compared to classical algorithms. So a qubit is just a mathematical abstraction of a quantum physical system that can be in two different states that, as usual, we denote in Dirac notation by ket0 and ket1. As you know, the general state of two-level quantum system can be in a superposition, this state phi, with amplitude alpha and beta, and you know that the magnitude squared of these two amplitudes needs to add up to 1. Okay, so in fact, a qubit, as a mathematician, I like to think of a qubit as just a vector in a Hilbert space of dimension 2, which is normalized. Okay, and you know that it needs to be normalized because when we try to observe the state of the qubit, when we need to, or we want to estimate the values of alpha and beta, we cannot directly access these amplitudes. We need to measure the state, and then if we measure in the computational basis, if we measure in the basis 0, 1, then we get either 0 or 1 randomly with a probability that is exactly the magnitude squared of alpha or and beta, depending on whether we get 0 and 1, and then the state collapses to 0 or 1. Okay, so this is the reason why we impose that these two magnitudes squared add up to 1. And one important thing to notice, something that is quite different from what we have in classical algorithms, is that, as you know, we cannot clone the state of the qubit. If we have a qubit in a general state, we don't know what is the state of the qubit, and we want to estimate the values of its amplitudes. Well, we could think of making different copies of this state and then measuring each of them and then estimating the values of alpha and beta. But there is this famous no cloning theorem that prevents us from perfectly copying, creating an independent copy of the state of the qubit. Okay, so this is something that is, at least for computer scientists, quite striking, because, well, you have, of course, in classical information processing, the possibility of copying information without any problem, without disturbing the state of the system. But in quantum computing, because we are dealing with quantum states, this is not possible anymore. Of course, we can also have not just one qubit, but several different qubits. We can have several different independent quantum systems capable of being in two different states, and the state of the whole system can then be in two different situations. It can be 0, 0, 0, 0, 0, 0, 0, 1, and so on. And of course, we can also have a superposition of all these possible states that we call basis states, and the general state for an n-qubit system is then a linear combination of all the basis states, again with this normalization condition, because when we measure the system, if we measure all the qubits at the same time, we are going to obtain one of the possible basis states, 0, 0, 0, 0, 0, 0, 0, 1, or whatever, with probability that is exactly the magnitude squared of the amplitude of that basis state in the general expression of the n-qubit system. So this is exactly the same situation that we had with one qubit, but now we have an exponential number of possibilities. And this is one of the reasons why quantum computing can offer some advantage over what is possible with classical computing, because somehow we can compute with an exponential number of possibilities all at the same time. It's not so easy as that. It's not so easy as that. I will mention this again later on. But at least we have this possibility of working with an exponential number of parameters. And in fact, the initial or the original interest in using quantum computers or developing quantum computers was stated by Richard Feynman, among others, to be able to study physical systems, quantum physical systems, in which the number of parameters that we need to take into account grows exponentially with the number of parts of the system. If we have an n-qubit system, then the number of states that, or number of amplitudes that we need to consider grows exponentially and becomes unfeasible to work with the system when n is, for instance, 100 or something like that. It's impossible to manage to the 100 amplitudes with a classical computer. Okay, so we have these quantum states, we have these systems with n qubits, we know how to measure them. We now need to be able to manipulate their states in order to implement useful computations. And of course, any transformation, any action that we want to do on a quantum system needs to obey Schrödinger's equation, okay? And as you know, the solutions to this equation are always unitary transformations, unitary linear transformations. Because when we evolve a system, a quantum mechanical system, of course, we need to have, after certain transformations, something that is still normalized. And the transformations that preserve this normalization, that conserve probabilities, are exactly the unitary transformations. In the case of quantum, the quantum circuit model, we are going to be working with discrete transformations that act on a finite number of qubits, on a finite number of dimensions. So in this case, we can associate to any possible transformation a matrix, which is a unitary matrix. So its adjoint is also its inverse. And this is what we call a quantum gate. A quantum gate is just a matrix, a linear transformation, which is unitary, and so and thus it preserves the normalization condition. Of course, if we have an n-qubit system, we could have unitary transformations of up to n that act at up to n qubits, but it's not so difficult to show that we don't need to be able to physically implement any possible unitary transformation. In fact, we can restrict ourselves to just a finite set of reduced set of gates, which allow us to implement any other possible unitary transformation up to certain error. Okay, and then this makes developing and constructing quantum computers a little bit easier. It's not easy at all, but it's a little bit easier than if we needed to implement any possible unitary transformation. And some of the most important gates that allow us to do this universal computation are shown here in this slide. We have one simple gate, which is the negation, the NOT gate or the X gate. This is one of the Pauli gates. Of course, we also have the Y and Z gates together with the identity. We also have the Hadamard gate, which is extremely useful because it allows us to create superposition. Then we also have this family of gates, which are rotations around the Z axis on the Bloch sphere. As you know, we can represent a two-level quantum system in the Bloch sphere, and these are just rotations around the Z axis. And then we have what is possibly the most important gate, or one of the most important gates in quantum computing, which is what we call the control NOT gate or C-NOT gate. This gate is very important because it's the one that allows us to create entanglement. Okay, and entanglement is necessary in quantum computing to have advantage over classical systems. If we have independent, non-entangled systems, then it is easy to simulate the behavior of the system with just classical resources. And somehow the power of quantum computing comes from the possibility of creating entanglement. It's not only that, because we know of certain situations in which we have highly entangled states which can be simulated classically, but at least is one of the ingredients that we need in order to have something that is not it cannot be simulated with classical resources. And in fact, these gates that I have shown here are enough to implement any unitary transformation up to the error that we desire. Okay, so we have these two theorems. Well, there are other universality theorems that I'm not showing here, but well, if we have, for instance, the H, X, one of the rotations, one of the rotations of the family that I have shown before, which is also called sometimes the T gate and the C naught gate, then we are good to go. We only need to implement these gates in order to have universal quantum computing. Okay. Any question up to this point? Well, I did not mention that, of course. Please feel free to interrupt me at any moment and ask any question. And of course, I will be also taking question at the end of the seminar. But if you want want me to clarify something, please feel free to unmute yourselves and speak up. Okay. Okay. So with this brief introduction, we already can see that quantum computing is a little bit different from what we are used to with classical algorithms. One could naively think that, well, in fact, this model of quantum circuits is just linear algebra, and in fact, we are just multiplying matrices times vectors, and then sampling from the final state taking according to Born's rule. And one could think that, well, this is not so different from classical computing because, well, this is just linear algebra. And well, it is true to a certain state, but you also need to think that the size of the vectors and the size of the matrices representing the gates that we are using here is exponential in the number of qubits. And this is one of the reasons why simulating classical computers is difficult, quantum computers is difficult for classical computers. But this is not the only reason. Of course, we also have the impossibility of copying information, as I mentioned before, and we also have interference and entanglement. And superposition, interference, and entanglement are the three main ingredients that you need to take into account to create a successful quantum algorithm. Of course, you also need to take into account that operations in this model are reversible, something that is not possible in general with classical circuits, but this is not a big difficulty because it is possible to transform any classical circuit in a reversible one just by adding a modest number of additional bits. We also need to take into account that this model is probabilistic, it's essentially probabilistic because when we measure the system, we obtain something that is random and follows a certain probability distribution, but this is not the main difference from quantum computers and classical computers. We can also think of classical algorithms that use random bits to a certain extent, and this is used, for instance, in many optimization algorithms and in artificial intelligence, in machine learning, in different ways with just classical computers. The main difference is the possibility of working with an exponential number of parameters. by means of by using superposition, the possibility of having interference, and the possibility of creating entanglement. Okay, and with these three key ingredients, we can define, or we can construct several different algorithms that are useful, are faster in some way than their classical counterparts. And I'm going to briefly mention some of them, and then I'm going to try to show some applications of these quantum algorithms and related ones in high energy physics. So the first one that I want to talk about is Grover's algorithm, probably my favorite quantum algorithm, which can be used to find elements that satisfy a certain condition in an unsorted list. So suppose that we are given a list of elements. For instance, I usually give this example that we have a telephone number, and we want to find who's the owner of this telephone number. And if we have a list of persons with their numbers, but this list is not sorted by number, but by name and last name, then for a classical computer, it's difficult to find the person whose number is the one that we are interested in, because there is essentially no other way than just trying to read the whole list in some order and try to find whose number is the one that we are interested in. With Grover's algorithm, we can speed up this search quadratically. If we have n elements, we can query the list of elements a number of times that is proportional to the square root of m, and find the element that satisfies the condition with high probability. Okay, so this can be used to speed up different processes. For instance, although I'm not working directly in that problem, I know that at CERN they are trying to use this kind of algorithm, and also at the University of Lisbon they are trying to use this kind of algorithm to speed up track reconstruction problems, tasks in particle physics collisions. And it can be used in any situation in which you need to search for something, which is almost any situation. Okay. Another algorithm that I have already mentioned that is very important for its implications in cryptography is Shor's algorithm, that allows us to find factors of large integers in time that is roughly n squared, where n is the number of bits in the number. And to compare, the best classical algorithm that we have today has complexity which is on the order of e to the square root to the third root of n. Okay, so this is almost exponential. So with Shor's algorithm, we would be able to factor these numbers in polynomial time, so efficiently, and we could be able to break these protocols which are now widely used in communications through the internet and in many different cryptographic protocols. Okay. Another interesting algorithm that is based on a similar idea to what is used in Shor's algorithm is the HHL algorithm that uses again the quantum Fourier transform, which is the main ingredient in Shor's algorithm, and was proposed in 2009, so not so long ago. And it allows us to solve or to obtain, to sample from solutions of a given linear system under certain conditions. Okay. And it has different steps that I'm showing here. The main one is this phase estimation that is done with the quantum Fourier transform that is shown here. And this is one of the ingredients of many successful quantum algorithms. It uses entanglement and interference to a high extent in order to speed up this computation of or estimation of the phases of the eigenvalues of a certain unitary transformation. So these are kind of the most important quantum algorithms that we have mathematically proven that offer some advantage over what is possible with classical computers, but they all have one main drawback that prevent us from using them with actual quantum computers. The problem of these algorithms, Shor's, Grover's, the HHL algorithm, is that they need a large number of qubits, but also qubits that are somehow resistant to noise, that are fault tolerant. If you have noise in your system, if you have noise in your quantum computer, this can prevent to a great extent the successful use of these algorithms. Okay, so it's estimated that, for instance, to successfully use Shor's algorithm to factor a large number, for instance, a 3,000 bit number, which is on the order of what is used in the RSA protocol, we are going to need on the order of several million qubits, because with these several million physical qubits, then we can construct several thousand logical qubits, which are fault tolerant. And then we can use these algorithms that require fault tolerant quantum computation. So this is something that we cannot do today. We expect to be able to do this eventually. For instance, companies such as Google or IBM have recently published roadmaps in which they state that they will be constructing quantum computers with up to 1 million qubits or something like that by the end of this decade. Well, this is something that we need to see. I really would like to see this happening, but as of now, we have only quantum computers which have up to maybe 100 qubits. But this does not prevent us from trying to find applications of these small and noisy quantum computers. John Preskill coined this term of noise intermediate scale quantum devices to refer to the kind of computers that we have today, and several different algorithms that do not require these conditions of fault tolerance to obtain useful results have been proposed in the last few years. And I want to spend the last part of the talk introducing some of them and showing how at CERN, collaborating with other institutions like the University of Oviedo and other universities and companies, we are trying to explore the applications of these methods in high energy physics. So one popular algorithm that was introduced a few years ago is what is called the variational quantum Eigensolver, which is a quantum algorithm that can be used to approximate the ground state of a given Hamiltonian. Okay, as you know, this is a very important problem, not only in physics and chemistry, but also because it can be used to solve also optimization problems. For instance, you can transform certain optimization problems, NP hard problems, into an instance of the problem of finding the ground state of a given Hamiltonian. And the idea here is to use what is called a variational circuit, which is a circuit in we have some free parameters that we can train. So we can somehow measure the system with different parameters and try to optimize to find the best parameters in order to solve a given problem. In the case of the variational quantum eigensolver, what we try is to find a state, a parameterized state that is obtained by setting an initial state and then using this variational circuit to evolve the state and create a new final state. And we want to find the parameterized state whose energy regarding this given Hamiltonian is the lowest possible. And this can be done in certain situations with the collaboration of a quantum computer and a classical computer. So this is an instance of what are called hybrid quantum algorithms. And in fact, most researchers in quantum computing expect the next few years to be mainly devoted to exploring the possibilities of these hybrid quantum algorithms, in which you don't do all the computations in a quantum computer, but just use the quantum computer as a kind of accelerator, similar to what we do, for instance, with GPUs, to solve certain niche problems that the quantum computer is better at than classical computers. In this case, roughly what we do is to prepare the parameterized state with the quantum computer, measure this quantum state. So we prepare it several different times and we measure it several different times to estimate its energy, and then use a classical optimizer on the classical computer in order to find the best parameters and then to reduce the energy and to try to approximate the ground state of this Hamiltonian. This has been used successfully with both simulators and actual quantum computers for chemistry simulation problems. This is taken from a Nature paper published 3 or 4 years ago, in which several researchers from IBM were able to obtain or to estimate the dissociation profile of several simple molecules with a quantum computer using this VQE algorithm. This is, of course, something that we can do easily with a classical computer, but somehow shows or highlights the possibilities of using quantum computers, even noisy quantum computers, for practical and useful tasks. And this has been also used in applications in high energy physics, for instance, to obtain the ground state and also excited states of this Rabi Hamiltonian, which I confess I really do not understand, because as I mentioned, I'm not physicist. I'm sure that you understand this much better than me. But the thing is that you can transform this Hamiltonian into a Hamiltonian that you can simulate in a quantum computer with a parameterized circuit similar to the one that we are showing here at the bottom of the slide. And then you can use the VQE algorithm in order to obtain the ground state and also excited states, because you can add here, once that you have the ground state, you can add here another term which kind of measures the overlap of a given state with the ground state, and then you can penalize somehow states which are similar to the ground states, and you can try to estimate also the first excited state and so on. And these are results found by researchers at Fermilab in using the VQE to obtain the ground state and the first excited state of this system. Another application of these variational circuits, which is one in which I am quite involved, is the use of these quantum variational circuits as a kind of machine learning method that allows us to classify different situations. and we can get inspiration from classical machine learning methods, like for instance, support vector machines, in which we try to find a hyperplane that separates points from one class and another. And we can extend this model also to work with non-linear separations by using what is called a kernel. The idea with quantum support vector machines is to use quantum computers, in particular quantum variational circuits, in order to implement kernels that are difficult to simulate with classical computers, and then try to exploit the possibility of working in this higher dimensional space to better separate the classes with these new kernels. This has been used by several different groups in problems regarding the classification of events in which the Higgs boson is produced. One of the pioneers in this direction was Xiaolang Wu and her group at the University of Wisconsin, together with other researchers from other institutions, including Federico Carminati and Alberto Di Meglio at CERN Open Lab. And they were able to implement these quantum support vector machines for the classification of Higgs events in these channels, and to show that you can obtain methods that are slightly better in classification power than classical methods, the best classical methods. The difference is probably not statistically significant, but at least it shows that you can do this with a quantum computer. What is more interesting to me is that they also shown that somehow these quantum methods seem to need less data to learn the separation between the different classes than what is needed with classical methods. And this is something that has been shown or has appeared in other experiments done by other researchers with other quantum machine learning methods in similar situations. Okay. Another way of using quantum computers for defining these quantum machine learning methods is the use of what are called quantum neural networks, which are again an application of these variational circuits, in which now we have two different parts. A first part that we call a feature map that we use again by using parameterized gates to encode classical information as a quantum state, usually a highly entangled quantum state. And then we have another set of parameterized quantum gates with trainable parameters that we can use to create a classifier that separates two different classes. Okay, and in this case, of course, we need to consider different possibilities for the variational forms, both for the feature maps and for the classifier itself. And there is a lot of research going on trying to determine what are the best options, what are the best variational circuits, what are the best possibilities to encode the states, and then to classify these data points with these variational circuits. And this is still not completely understood. We still don't know whether these variational circuits offer some kind of advantage over what is possible with classical neural networks, for instance. But there are certain recent results that seem to show that, in fact, by using these quantum neural networks, you can access functions or have the possibility of expressing more functions than what is possible with classical neural networks. So to me, this is a very interesting topic and one of the hot topics in quantum machine learning nowadays. And this is something that we have been exploring on the line of all the different experiments, for instance, the ones performed by Koji Terashi at the University of Tokyo, in which these variational circuits were used to classify again events involving the creation of Higgs bosons in particle collisions. And again, it's interesting to notice that although here we don't seem to find that these variational circuits offer the best overall performance, at least for a reduced data set, they clearly outperform what is possible with classical networks. And this is something that we have been exploring in collaboration with CERN, in collaboration with researchers also from ETH Zurich, in again situations in which we have particle collision events, and we want to determine whether the Higgs boson was produced or not. And here in this recent paper, we explore different ways of reducing also the dimensionality of the initial data in order to be able to use actual quantum computers, which are still, as I mentioned, quite small. And we tried different architectures for quantum neural networks and different kernels for the quantum support vector machines. And our results are consistent with what I have shown before, obtained by other research groups. Finally, I want to show another application, which is the use of quantum variational circuits to implement a quantum version of generative adversarial networks. I don't know if you are familiar with this neural network model, but the idea is to use two different neural networks. One is called a generator and the other one is called a discriminator, which are trained together in an adversarial way. The generator is trying to fool the discriminator, and the discriminator is trying to distinguish the data, the artificial data produced by the generator from the real data of a distribution that we want to be able to sample from. This distribution is generally unknown and is difficult to simulate analytically or to sample from analytically. And with these neural networks, in the classical case, impressive results have been obtained, for instance, to create phases that are completely or almost completely real. These phases that I'm showing here are created by an artificial neural network trained in this way with a GAN model. And several different researchers have proposed the idea of replacing one or both of these classical neural networks with quantum variational circuits in order to obtain quantum generative adversarial networks. This is something that has been explored by researchers at CERN Open Lab in order to reproduce the output of calorimeter detectors in deaccelerators at CERN. This is something that they had done already with great success with classical generative adversarial neural networks to replace, for instance, Monte Carlo simulation, which is computationally more expensive. And the idea here was to try to see to which extent quantum generative adversarial networks were able to reproduce the same kind of result and eventually offer some advantage. The problem with this architecture is that it's much more difficult to train than just classical neural networks. And preliminary results by Sujong Chan and Sofia Vallecorsa show that at least in a qualitative way, it is possible to reproduce the output of these calorimeters with these quantum generative adversarial neural networks. Of course, we need here to reduce the dimension of the data in order to be able to work with simulators or with actual quantum computers, but at least this is promising. And one project that I've been involved with in the last few months is to try to extend this application of quantum generative adversarial neural net to not only generate average situations like this one here, but to generate independent outputs of the calorimeter, independent images representing independent events in the particle accelerators. And this is something that we have been doing together with researchers from the University of Cambridge, from a company called Cambridge Quantum Computing, and with researchers from EPFL. And we have some initial results. Now we are trying to reproduce these results that we obtained with simulators also on quantum actual quantum devices. You can check some of our results in this recent paper. So, well, this was more or less what I wanted to show you today. I want to mention that all these initial experiments have now been somehow collected under this umbrella that is the CERN Quantum Technology Initiative, which has several different branches in quantum computing, in quantum communications, in quantum sensing, in quantum simulation. This is quite ambitious initiative developed by CERN, which tries to also act as a hub of quantum knowledge and quantum computing resources across Europe. As Javier mentioned at the beginning of the talk, I'm the Spanish representative at the advisory board of this Quantum Technology Initiative. And in the next few months, an official announcement with a roadmap for the next few years will be made. As part of this CERN Quantum Technology Initiative, last year when I was at CERN for several months, I gave this online introductory course that you can find online, starting from scratch, introducing the model of quantum computing, of quantum circuit models, and explaining how to program quantum computers, how to implement quantum algorithms like the ones I have been telling you about. And if you are interested in knowing a little bit more about these technologies, I invite you to check these lectures that are available for free on CERN's YouTube channel. And well, thank you for your attention. And if you have any question, I will be happy to answer any of them.
So first of all, we want to thank Elías